Alright, welcome to the final chapter of Introduction to Networks. This is basically where we concentrate on filling in the rest of the command structures required for building a basic network. So at the end of this, combined with the previous chapters, you will be able to create a network consisting of a couple of host machines, a switch, and a router. Okay, so just a very basic network using Packet Tracer. So we'll get stuck into it because once we get the theory out of the way, we can spend some time doing some lab work. Okay, so this one, as I said, we have the final input into configuring our small network. We'll look at some of the protocols we use for identifying various items throughout the network, verifying connectivity, how we can scale this up fairly easily if we use the correct modular methods. And then we'll come back down to the usual troubleshooting methods and scenarios at the end. So we've all kind of built a small network at home, and which basically represents what we're going to be doing here. I mean, you think about it, your home router is a router as well as a switch. They all have a built-in switch, and you connect host machines to that device via the switch. So you've already done a basic network by the simple fact that you've configured your home network. So this is what we're representing here in the small network. We have a WAN connection, which is our connection to our ISP, and the only difference between our home network and the enterprise network is the fact that we scale it. Okay, Christopher is saying he's got no audio. What about the rest of you? You're hearing me okay? Yeah, all right. Just checking to make sure it wasn't my end. All right. No, I think you're right the first time, Jacob. You put up with me rambling. All right. So one of those days I'll remember to turn that thing off. So while we're waiting for Christopher to rejoin, we'll just do a quick. Oh no, he's there. Who do we drop? There he is. He's now there twice. Isn't that nice? Can you hear me now, Christopher? Maybe. Oh. Okay. So, continuing on, you haven't missed much in the first couple of slides, not hearing my lovely voice. All right, so the main difference between the one that you do at home and the one you do in a small business is the cost and the features of the equipment. So when you scale up, you need, for switches, you need more ports, and most switches have fixed port types. So They'll either be fast Ethernet or gigabit or whatever your requirements are. And because you also need to buy a chassis that has the number of ports plus some room for expansion, you increase the capabilities of the device from your home office, so it's going to cost you more. Okay, so that's the cost and the types of ports and interface differences. And when we come up to that WAN interface, we tend not to connect via the same connection out to our ISP. They'll tend to give us a different type of connection. And because we're scaling up, we've got greater capacity to expand, and because we need bigger and more optioned devices, we'll have operating systems that have larger scopes of features and services available in them. So it's pretty easy at home. We just sort of turn on the DHCP server and everything's kind of like plug and play. Now, with our network's design and implementation, we need to define our IP addressing scheme. And when we're looking at a small office environment, we'll have servers and peripherals, i.e. printers, security cameras, things like that, that will need IP addresses statically assigned. So when we create our addressing scheme, we need to create it in a manner that we can assign a block of addresses via static addressing, and then a block of addresses we use for hosts as they join via the DHCP pool. Now, part of that static addressing scheme has to cater for, as I said, the servers, the printers, security cameras. Our routers and switches also need to have those static addresses assigned to them as well. It's always a good idea to have all of this documented, because you need to refer back to it later on, because it's not every day you set these up. So if you document what you're planning to do and leave some addresses in there for expansion, like new servers, new printers for the company to grow, and you'll get an idea of that growth prospect by talking to the management of the business. They'll have a growth plan, the forecast for 5 years. So redundancy. It would be lovely if we could all have fully redundant networks, but the reality is it's not going to happen, because a fully redundant network means we have duplicate static devices. So 2 routers, 2 switches, 2 servers, onwards and onwards. So, and all the cabling has to be redundant as well. So this is our design goal, fully redundant systems, but the reality is it's not always possible to get there. Like your average small enterprise won't have double redundant routers. You'll have a single point of failure with the router connecting to your ISP, but you'll probably have redundant switches and servers within your enterprise. So that's the trade-off between your redundancy, reliability, and financial capabilities of the firm. Okay, because remember, everything comes back down to the budget that they're prepared to supply. A second link out to a separate ISP, well, that's just duplicating our money again. All right, traffic management, otherwise referred to as quality of service. So keep in mind that it's good to design your network with this in mind, because at some stage you'll have to prioritize traffic within a network. All right. So the standard types will have voice being the high priority, file transfers, storage, that sort of thing being low priority. Under your highest priority for voice, you'll have transactional traffic. So if you're working for a company that has a some form of retail attachment or wholesale attachment, selling goods, so that traffic attached to the business of selling and keeping track of sales is known as transactional traffic, and as that's how the business earns money, you have to give that higher priority as well. All right, so you break it down into high, medium, null, and low priority traffic, and you assign queues so that the traffic is serviced in a ratioed fashion normally. Okay, so when voice traffic comes in, it's the VIP, it gets instant service, and then normally the rest of the traffic is ratioed in some form to balance the traffic out. Like you might give three medium priority packets, then 2 normal, then 1 low, and then cycle back up, that sort of thing. Common applications within the network. Well, by now we kind of know that we have network applications and applications that are using the network. Okay, so the network applications are basically the ones that allow us to manage the network, if you like, and they gain access to the network resources directly. Whereas application services, which are the ones that are on your host machines and they need to get somewhere, but they don't talk to the network directly, they have to go through this layer services to gain access. So some of the common protocols will be Telnet and Secure Shell. So these things we use to communicate to our devices to do our configuration. Then we have email, which is our simple mail transfer protocol, post office, IMAP, and I'm really hoping this is all second nature to you, because this should be reinforcing the IT essentials materials that we went through as well. File transfer protocol and secure file transfer protocol can be used to transfer files between 2 destinations. We've gone over DHCP and DNS a few times in different units so far, so we'll just move on from there. All right, common protocols are basically the ones that make up core networking. They're the things that we use on a daily basis without even thinking about it. So they're going to be our HTTPS, our SSH, file transfers, email, so our SMTP and POP, that sort of thing. All right, so voice and videos became a big thing about 10 years ago. They used to be on a separate network infrastructure. Now everything's migrating across to a common IP infrastructure base. So our voice is no longer on a separate network with separate protocols. What we do now is we transport it over IP, so voice over IP, which Cisco call IP telephony, which bundled into that is they have their dedicated quality of service, call control and signaling and everything to make that happen. And then you have real-time applications and the protocols that handle that real-time communication that you need in place for video conferencing and voice calls and things like that. So growth is going to occur under normal circumstances. So you need to have some capacity within your network to expand when you do the initial design. And to keep track of everything, you need good documentation. So you need physical and logical topology documents that show you where things are physically located, how they're connected to each other, and then a logical topology that shows you how the traffic flows between the devices and the IP addresses and that sort of thing. Next, you need basically a record of all your devices within your network. So this inventory will list the make, model, serial numbers, and characteristics of each device. Budgets have to be maintained. Equipment needs to be maintained. You need to have a budget to replace faulty equipment. You might have service agreements with providers, that sort of thing. So you need to always cater for your budget and have line items in it to provide for natural growth. So adding switches to increase user numbers, adding servers. Now, big ticket items like major expansions and things like that, you'll get a separate project budget. But on the day-to-day use, your maintenance and consumables, so your print cartridges, toner cartridges, cables, that sort of thing, will come out of your line items for everyday budget. Traffic analysis you should do on a regular basis, a couple of times a year at least, and this helps you plan your network traffic. So you can see, if you're analyzing your traffic, you can see if certain applications are consuming more resources, and you can forecast how long before your available resources cannot support those applications any longer. So you'll need to plan for upgrades and things like that. So how do we analyze the traffic across the network? Well, first thing you do is you capture the traffic. In other words, you take a copy of it as it goes through a point in the network, so you can analyze what is going on. And then you look at what the traffic type is within that capture sample, where it's going to and from, and you basically can determine whether a certain application is being more used than was originally planned. So you may have added an application into your network sphere, and then that needs to be monitored to see the uptake, and at some point it will saturate it, and like for example, you might have more and more employees come into the firm and suddenly your bandwidth's no longer capable of running that application across the entire network because switch ports are no longer up to it. For example, you had a 10 megabit switch, you might have to go up to 100. Right? You will come across old hardware out there. Not every business is going to be having the latest and greatest out there. Businesses tend to only upgrade equipment when they're forced to. So, employee network utilization, and when we look at this we need to take a capture of workstations and servers and that, and have a look at what versions of operating systems we're using, how much CPU is being used, RAM, drive. So basically everything that combined can impact the performance of any particular device within the network. We need to take snapshots of how they're performing, and we need to keep this on file so that we can refer back to it the next time we come up to review what's going on. So it gives us some history across the network. Verifying connectivity, so we're hopefully all familiar with the ping command by now. So this basically uses the ICMP protocol, the echo and echo reply functions within ICMP to ping from point A to point B. Now the standard outputs for the ping command, exclamation mark indicates successful reply message being received. So you've got good layer 3 connectivity between the two devices. A period means a timeout has occurred, which could indicate a problem within the network path somewhere. It could also indicate that an ART request had to be made to determine that layer 2, layer 3 partnership, which could cause the delay. So if you get one or two periods in your ping, I would repeat it and see if it continues. Okay, because quite often you'll get 3 or 4 exclamation marks in the very first time you do it, and if you repeat it again in a short order within a couple of minutes, you will get all 5. Okay, so just be aware of that. U indicates that a destination unreachable reply has been sent to you, which means basically a device doesn't know how to route the traffic to get to the destination network. So Cisco operating system, so pinging from a Cisco router or a switch, if we just hit the enter command after ping, it goes into extended mode. And what this means is we can specify the protocol to use, the target addressing, how many echoes requests to send, the size of the packet, our timeout sequence, and extra functionality as to, we can specify the source of the request. Okay, if you're using a standard ping on a Cisco device, the ping will originate from the interface closest to the destination. So you can actually specify the opposite side of the device, for example, for the reply. So it knows it has to know that network, that sort of thing. Traceroute is used to determine if there's a problem somewhere along the path. So a ping will just tell us that we've got connectivity from A to B, or if there's an issue. If there's an issue, we follow up with the traceroute command, and this will tell us what layer 3 device we get to in the path to the destination. And if we only get to router 1, we can assume there's a problem between router 1 and router 2, for example. Okay, and this is the traceroute output. So this is telling us that we've got 2 milliseconds to this device, and then we've got timeouts. Now, some of these devices will not give you stats because some of their functions within ICMP and that are turned off. Like they won't respond with the names of the devices and things like that. But you should have a response because you know when you've sent it timestamp wise and when it was received. So you'll get some feedback if you're getting there. If it doesn't come back like it is here, request timeout, timeout, you can cancel it with the Control-C, and you know the issue is between your device and after this device. So, for example, here we have our sequence there. It's telling us it's gotten to this first hop, this second hop, and then the third hop. So, like with the ping command, we can use an extended traceroute. So these are all the different hop options we can include. So we can force it to IPv4, IPv6. We can do a host list. We can specify the maximum hops that the path can take whilst using the traceroute. Okay, and we can even tell it not to bother to do DNS record lookups on the host names for the IP addresses of the various devices that it encounters. And here's an example of what that looks like when you're setting it up. So as you can see, it's basically the same as the ping command in that it will go through and give you a lot of questions, and the default answer, if you just hit enter, is in the square brackets. After building a network, you should take a network baseline. So this is basically taking results of your ping and trace commands and putting them into text files and that to be archived. Any error messages and things like that that you encounter, all of these things can be used to determine the differences between 2 points of time when you check them periodically. Now, there's more advanced and intensive ways of doing this, and there's specific tools out there that allow for the monitoring and testing of a network. Obviously, these tools generally have $1 attached to them. So if you're doing everything on the cheap, then the simplest way is to make sure you do your cut and paste from your ping and trace commands into a text file. So it doesn't have to be complex, you just have to have some form of measuring of the performance. Alright, as we start to get into the interesting part of the day, how to configure devices. Now, I'm going to assume that we're all familiar with IFconfig /all from testing our host machines during the day, and we've lost tape. So with this we can go through, do our usual checks, make sure our DHCP and DNS and all that is being resolved within the configuration of any host machine, and the same can be done on any Linux addresses with the IFconfig. Now, depending on the version of Linux, some of the new commandlets, one of them is IPADDR for the IP address command rather than IFconfig. So it just comes down to the versioning and that of your operating systems. Okay, so there's the Mac. Not going to spend any time on Macs. We don't have any to use as examples in classroom. Address resolution protocol command. So if we want to look at how our device has the ARP table, so with the ARP-A command, you could see the match between IP addresses and MAC address bindings within the host. And we can clear it by using the netsh interface IP delete ARP cache command, which would basically clear that table and force it to be repopulated with new information. So our basic commands that we should know by now, if you've been doing the associated labs that are attached to the chapters, you would have the show running config, show interface, IP interface, ARP, IP route, protocols, and version commands. Forget it. You'll be familiar with those commands. And the next one you may not have used is the show CDP Neighbors command, which is a Cisco discovery protocol, and this only works between Cisco devices at layer 2, and it will tell you information about the device, its address, the port numbers, its capabilities, and platform. So basically it will tell you whether it's a switch or a router or something else. But in what we basically will be looking at is switches or routers. It'll give you its host name, the interface ID that it's used to connect to that device, what port number it connects to at the other device, and what platform it is. So in this example here, it's saying that we can see switch 3, S3, we connect to it via gigabit 001, and our time hold down before this entry expires is 122. It has switching and IGMP capabilities. It's a WAN switch C2960 plus, and we are connected to it on its fast Ethernet 05 port. Now, if we add the details option at the end, we get to see additional layer 3 information on that neighbor. Show IP interface brief will tell us what interfaces we have that are configured at status, basically. So summary status. So here's the interface names, whether they've got an IP address assigned to them, whether everything's working for them, the method of configuration, manually or automatic or not set, the status, whether it's up or down, and that is the layer 1 status. So in other words, does it have a circuit? And then the protocol is basically layer 2. So basically it's saying I have my little base signal going between the 2 ports, and I have the basic protocol communication between those 2 ports as well. Basic troubleshooting approaches, same 6 as what we've been used to in IT Essentials. You identify the problem, establish a theory about what could be the cause of the problem, you test your theory. If it fixes, all good. Establish a plan of action to implement your solution. You may not be able to implement your solution during business hours. You might have to schedule a maintenance window. Verify and implement all of that in place. And then once you've verified it all and it's all working, you document everything that you've done, the symptoms, what process you used to confirm your findings, and what you did to rectify it. And you record this for future reference to speed it up later, because if you have it, most companies now have a common knowledge base. So by you documenting your findings, the next time it occurs, it might be somebody else, and they can find your solution quickly and easily in the database. Now, remember, you're generally working as part of a team. So while you're learning, if you can't find the issue, you escalate it up to another tech within the structure. Okay, so senior techs and that sort of thing. You'll see in a lot of help desks, they'll talk about level 1, level 2, and level 3, and that basically means the knowledge of these individuals. So level 1 are the incoming calls, doing the jobs, getting the basic information, just using the script kiddie. So knowledge base to answer the questions, simple things. If they can't resolve it on the line, they escalate you to a level 2 technician that tries to troubleshoot it more thoroughly. And anything they don't know, they escalate it up to the boss, which is level 3. Now, Debug Command is a very powerful tool. It allows for you to display ongoing messages within your device. And yeah, Jacob, that's good. So the debug allows you to see what's going on in real time. Using the show commands, it only takes a snapshot of what the status was when you took the show command. So when you put the debug command on, like if you go debug OSPF, then, for example, it will show you every OSPF packet type going and coming to your device as it occurs. So it's very good for fault finding, and I say OSPF will be looking at protocols in the next series of cluster of units, which we will talk about IP protocols and switches in more depth, and we'll come back and look at the debug commands in that vogue as well. Now, using this command is resource intensive on the device. So once you've captured your information by watching the output of this debug command, it is recommended that you turn it off as soon as possible by using undebug. So debug turns on the command, undebug turns it off. Now, you need to use the same options after the debug that you used to turn on. So if I said debug OSPF 1, I would have to go undebug OSPF 1 to turn it off. Or you could use the generic undebug all command that turns off all debugging on the device at once. And this is an example of the debug command. So one of the nasty things with Telnet and other remote connections is the monitor command doesn't transfer all message types to the remote connections. So in this example here, we have sequence up here. We're not getting all of the information. So we've turned ICM packet debugging on, and we did a ping command, but we saw no debugging commands output. So what we did was we turned terminal monitor on, which means to push out all the message types out to the remote display. And now if we repeat the ping command, we see the echo reply being received. Okay. All right, duplex mix match issues. This used to be very common. It's not so much anymore. But basically what happens is the one end says to go dual or full duplex, okay? And the other one says, no, I only want to be half duplex. In other words, one's only sending or all receiving and the other one's sending and receiving. So because the two ends can't agree, they keep flopping back and forth. And your link goes up, goes down, goes up, goes down. Okay, so the way to fix this is to configure one end to be static, full duplex or half duplex, depending on the device configuration. By fixing one end, the other end will eventually agree with that configuration and stabilize. Now, one of the things you need to be aware of in this command is this is a summary of address. Now, what you don't see here is the corresponding subnet mask that goes along with that IP address. So you might have typed in the correct IP address, but mucked up the subnet mask, which means it won't connect to the other end because they're not the same network, even though they would appear to be using this command. So use the show IP interface brief command just as a summary. If you're still having issues with connectivity, use the more concise show IP interface command and specify the interface that you want to look at. That way it will give you more information about the configuration on that specific interface. Okay, if you see a 169.254 address come up on a end device, it's using the pipa addressing, which basically means it's an internal automatic assignment of address space. It hasn't actually connected to any other systems to give itself a DHCP, for example. So if you lose power in the office, for example, the time it takes for a switch to fully boot up and go through its listening, learning, and then forwarding process on all of its ports is generally longer than what a request timeout period is. So your host machines will generally go, oh, I can't find a DHCP server, I'll just give myself an IP address so I can finish booting up properly. You will then, after all your switches and that are powered back on, you'll have to go around and basically reboot the IP config on all these host machines by doing an IP config release and renew and get in contact with your correct DHCP server. Default gateways are your way off your network to the rest of the world. Again, just to be sure, what you see in the GUI in the interface config is what you wish it to be. It is not necessarily what has been pushed to the network card. Your IP config command will interrogate the card itself. Okay, so GUI shows you what the operating system believes it should be. The command prompt IP config tells you what is actually there. So make sure you know the distinction between the two. And make sure that you have an entry for a default gateway, or else you'll not be able to leave the local network. And use the ping command to make sure you can communicate with it. Okay, it's pretty obvious when we don't have connection to our DNS server because we don't get our domain name conversion. So when we type in a fully qualified domain, i.e. www.microsoft.com, it just comes back and goes, what? Alright, so it's pretty obvious when that's not occurring, so we can check again with the IFconfig to make sure we have an entry. And if we do have an entry, we then follow it up with a ping command to find out whether we've got connectivity to it. And if we've got connectivity, then we can use the ns lookup command to help troubleshoot specific information on the query and response of any lookups. Alright, so we went through and finalized some of the design issues with addressing schemes and features and scalability within networks. We talked about the difference between normal traffic and real-time traffic, in that voice and video conferencing, for example, needs real-time traffic support, and we need prioritizing, so quality of service, to enable that to go through first. And we talked about having good documentation within the network. We then addressed our testing, so we looked at ping and trace rate commands, both standard and extended, and then addressing issues and confirming our addresses on our host and intermediate devices, so that we can look at individual device configuration to see if the configuration is correct. And we talked about the differences in command sets used between the different operating systems used. We looked at the requirement of having a layer 2 and layer 3 address pair, which is known as the ARP table for address resolution protocol, and that will bind an IP address and a MAC address so that communication can occur. That is it. So the good news is there's some labs attached to this unit. So when you go through your reading and that, you'll come across associated videos and labs, and make sure you can do the challenge labs. Okay, the challenge labs in this unit basically tie everything together. So our basic configuration, our password securities and that we looked at, user accounts, setting up a local user account, that sort of thing, securing our device, auto secure, all that sort of stuff, and then configuring your interface IP addresses and all that are there. So please do all those labs, and because it all ties it all together, so we can tie off a basic network.